Okay, we're going to continue on with section, um, this is section 8.3, situations involving kinetic friction. And we'll start with this. In the interest of time, I'm going to skip some slides, so I'll slide through them. You're welcome to study this in the book, but I'm not going to hold you responsible for it. So you consider the book sliding to the right on the surface of the table and slowing down due to a friction force, as in the figure. The work done by the friction force on the book, uh, there's work done by the friction force on the book because this is a force and a displacement. The equations for work involve displacement of the point of application of the force. Now, they modeled this as um, a single point of contact. It's a very simple, to me, kind of an oversimplification because there's lots of contact points, but they're trying to make a point and trying to derive, and I'm going to skip all these derivations until we get down to basically, if you look at that bottom line, the work of the sum of the work of other forces plus the friction force times dr is equal to the change in kinetic energy. If you skip all the stuff in the middle, you see the sum of the work uh, sum of the work of other forces plus integral of the friction force times dr is equal to the sum of is equal to the change in kinetic energy. And so we're going to skip all the way down to this slide where it simplifies the equation. On the left side of this equation, we have the work of other forces plus Fk, the kinetic friction force, and dr. They'll be in opposite directions for every increment dr path followed by the object. So Fk dot dr is equal to minus Fk dr. So we rewrite it like this. So the magnitude of the kinetic friction force is constant and can be brought out of the integral. So the remaining integral of dr is equal to the sum of the increments of length along the path. So the total path length is d. And so W represents the work done on the object by all forces other than friction. And the equation can be used when friction force acts on an object. The change in kinetic energy is equal to the work done by all forces other than friction minus a term FKD associated with the friction force. And that's the bottom line of where I wanted to get. You're welcome to go through all the derivations if you want. I don't think they're really necessary, but if you feel for completeness you want to, that's fine. Okay, let's go back to the example. Consider the sliding book. Identify the larger system of the book and surface as the book slows down under the influence of friction alone. No work done across the boundary of the system by other forces. So the system does not interact with the environment. No other types of energy transfer occur across the boundary of the system. Assuming we ignore the inevitable sounds that the sliding book makes. The energy conservation equation is delta K plus delta E internal equals 0. So the change in kinetic energy plus the change in internal energy is equal to 0. So we write minus FKD plus delta E, the change in internal energy, and we solve. I can't see that on mine because my little image is covering it. The internal energy is equal to the change in internal energy is equal to FK, the kinetic friction, times the distance. Okay, so the increase in internal energy is the product of the friction force and the path length through which the book moves. Now, the path is important. You know, if we look at conservative forces like gravitational force, the path taken doesn't matter against gravity. A friction force transforms kinetic energy in a system into internal energy. So there has to be movement in order to get internal energy increase. If work done on the system by forces other than friction, then we write, I must have already, oh, I moved the thing. There we go. Work done on the system by forces other than the friction is equal to work equals the change in kinetic energy plus the change in internal energy. Um, so the reduced form of energy conservation equation represents non-isolated system model for energy for a system within which non-conservative forces acts, friction being a non-conservative force. Okay, quick quiz. You're traveling along a freeway at 65 miles an hour. Your car has kinetic energy. You suddenly skid to a stop because of congestion in traffic. Where is the kinetic energy your car once had? A, it is all in internal energy in the road. B, it is all internal energy in the tires. C, some of it has transformed to internal energy and some of it transformed away by mechanical waves. It is all transferred away from your car by various mechanisms. Well, the answer is C. The brakes, tires, and the roadway are warmer, so their internal energy is increased. In addition, the sound of the skid represents transfer of energy away by mechanical waves. The screeching tires, those are mechanical waves, and that's energy coming from your stopping the car. Okay, let's look at an example. A 6-kilogram block initially at rest is pulled to the right along a horizontal surface by a constant horizontal force of magnitude 12 newtons. Part A, find the speed of the block after it is moved 3 meters if the surfaces in contact have a coefficient of kinetic friction of 0.15. Now let's conceptualize this. The rough surface applies a friction force on the block opposite to the applied force. As a result, we expect the speed to be lower than if the surface were smooth. So we categorize this as follows. The block is pulled by a force and the surface is rough. So the block and the surface are modeled as a non-isolated system for energy with a non-conservative force acting. Okay, so let's continue. The figure illustrates this situation. Neither the normal force nor the gravitational force does work on the system because their points of application are displaced horizontally. In other words, there's no vertical movement up or down. Okay, we write the appropriate reduction of the conservation of energy equation, and that's delta K, change in kinetic energy, plus change in total energy, or change in energy equals the work. Okay, we find the work done on the system by the applied force, noting that delta X equals D because the motion is in a straight line. So work is equal to F delta X equals FD. There's no cosine theta because it's all in line. We apply the particle equilibrium model to the block in the vertical direction. In other words, since there is no movement, all the forces in the vertical direction equals 0. So the sum of F and Y equals 0. That means that the normal minus mg equals to 0. So N equals to mg, the mass times the gravitational acceleration. So we find the magnitude of the friction force using, you remember, the kinetic friction force is mu sub k times the normal, so it's mu sub k times mg. Substitute energies and solve for the final speed of the block. So the final kinetic energy is 1/2 mv final squared plus the friction force times, that's mu sub k mg times the distance d equals the fd equals the work. So v equals, if you solve for that, v equals 2 divided by m times minus FKD plus F delta X, which is FD. Now, the difference in the kinetic energies between a block sliding on a frictionless surface and the block in this example is equal to the increase in internal energy of the block surface system in this example. I didn't substitute the numerical values. If we do that, we come up with it's 1.8 meters per second. You can calculate what it would be if there were no friction, and see that it's you have all the information there. A 6 kilogram block, 12 newtons, 3 meters. But assume the friction is 0, and you'll get the speed. If there is no friction, then you'll see that the speed should be greater. Okay, now let's add an angle in here. Suppose the force F is applied at an angle theta, as shown in the figure. At what angle should the force be applied to achieve the largest possible speed after the block is moved 3 meters to the right? Okay, you might guess that theta equals 0 would give the largest speed because of the force would have the largest component possible in the direction parallel to the surface. Think about F applied at an arbitrary non-zero angle, however. Although the horizontal component of the force would be reduced, the vertical component of the force would reduce the normal force, in turn reducing the force of friction, which suggests that the speed could be maximized by pulling at an angle other than theta equals 0. Now let's categorize this. We modeled the block and the surface as a non-isolated system for energy with a non-conservative force acting on it. So I want you to look at that F and theta. The horizontal component to the right is F cosine theta, and the vertical component is F sine theta. Okay, there's a W there for a reason, because the original notes had an error, and I don't know how to make it come in time, so it's there waiting for the rest of the equation. Let's see, we write the appropriate reduction of the conservation of energy equation. That's the delta, the change in kinetic energy plus the change in internal energy is equal to the work. Now, we know that work is equal to F delta X cosine theta. That's our definition of work. It's FD cosine theta. That's the work done by the applied force. We apply the particle in equilibrium model to the block in the vertical direction. The sum of the forces in the y direction must equal 0. Well, it's the normal force plus F sine theta. Remember, I told you to go over here and look at the vertical force. Since it's opposite, it's F sine theta. And the mg is just the normal. The sum of those forces equals 0. Okay, I lost my place. Let's see, 1, 2, 3. Okay, solve for n, the normal force, and we see that n equals mg minus F sine theta. Now, substitute the energy changes and solve for the final kinetic energy of the block. And this is where I put in a W, because it should have said kinetic final minus 0 plus FKD equals work. They didn't, so I put the W in front. Now, solve for, and let's substitute the energy changes and solve for the final kinetic energy of the block. So we're solving for K final. You end up with FD cosine theta minus the kinetic coefficient of friction times the normal times D. Well, what is the normal? The normal is mg minus F sine theta, 2 equations above. We get that Kf is equal to Fd cosine theta minus mu K times mg minus F sine theta D. Okay, that in parentheses is just the normal, the new normal. Maximizing the speed is equivalent to maximizing the final kinetic energy. Consequently, we differentiate the final kinetic energy with respect to theta and set the result equal to 0. So dk final d theta get the derivative of it, and you, let's see, do I have any notes on that? FD, if you factor out the FD, you get the FD parentheses minus sine theta plus mu k cosine theta. You divide both sides by FD, it disappears because on the other side is 0. So you end up with minus sine theta plus mu sub k cosine theta equals 0. None of this, and this is just looking at my notes, none of this is on the PowerPoint. So mu sub k cosine theta equals sine theta. The minus disappears because you subtract sine theta from both sides. And so the mu sub k is equal to sine theta over cosine theta. We're dividing both sides by cosine theta to isolate the mu sub k. So the tangent of mu sub k is equal to theta. I got to catch up with where I'm. There it is. Theta equals tangent inverse of mu sub k equals tangent the inverse tangent of 0.15, and you come up with a 8.5 degrees. Okay. Notice that the angle at which the speed of the block is a maximum is indeed not theta equals 0. When the angle exceeds 8.5 degrees, the horizontal component of the applied force is too small to be compensated by the reduced friction force, and the speed of the block begins to decrease from its maximum value. Okay, let's see. Now, here's another example. A block of mass 1.6 kilograms is attached to a horizontal spring that has a force constant of 1,000 newtons per meter, as shown in the top figure. The spring is compressed 2 centimeters, 0.02 meters, and is then released from rest, as in the bottom figure. Calculate the speed of the block as it passes through the equilibrium position, x equals 0, if the surface is frictionless. So we're looking at the idealized case where there's no friction. So this situation has been discussed before, and it is easy to visualize the block being pushed to the right by the spring and moving with some speed at x equals 0. We identify the system as the block and model the block as a non-isolated system for energy. In this situation, the block starts at V initial equals 0 and x initial equal minus 2 centimeters, minus 0.02 meters. And we want to find the velocity of F at xf equals 0. We write the appropriate reduction of the conservation of energy equation. Let's see. That's just what we want. We write the appropriate reduction of the conservation of energy equation for the block being pushed by the spring. Change in kinetic energy is equal to the work done by the spring. Find the work done by the spring on the system. Work is equal to 1/2 kx squared max. We substitute the expressions for kinetic energies and work. 1/2 V final squared minus 0, because it was initially at rest, there is no initial velocity. That's equal to 1/2 kx squared. So we solve for V, that's equal to x max square root of km. Let's substitute the numerical values. 0.02 meters, the square root of 1,000 newtons per meter divided by 1.6 kilograms, and you end up with a velocity of 0.5 meters per second. Now, although this problem could have been solved in Chapter 7, it is presented here to provide contrast with the following Part B, which requires the techniques of this chapter. In other words, we're going to introduce a friction coefficient. Now, calculate the speed of the block as it passes through the equilibrium position. If a constant friction force of 4 newtons retards its motion from the moment it is released. Now, the correct answer must be less than that found in Part A, because the friction force retards the motion. So it's got to be less than 0.5 meters per second. Okay, we identify the system as the block and the surface, a non-isolated system for energy because of the work done by the spring. There is a non-conservative force acting within the system, the friction between the block and the surface. Now, let's analyze this. We write the appropriate reduction of the conservation of energy equation. Delta K, the change in kinetic energy, plus the change in internal energy is equal to the work of the spring. We substitute for the energy changes. 1/2 mv final squared. There is no v initial, so that's -0, plus FKD equals the work of the spring. When we solve for v final, if you go through that, you'll see that v final equals the square root of 2 over m divided by the work of the spring minus FKD, the kinetic friction times the distance, d. Let's put in, let's see, what did I, oh, the work. You substitute the work done by the spring, that's 1/2 kx squared max. You substitute the numerical values, and you see that the 0.39 meters per second is indeed less than the 0.5 meters per second found in part A. What if the friction force were increased to 10 newtons? What is the block speed at x equals 0? In this case, the value of FKD as the block moves to x equals 0. Which is equal in magnitude to the kinetic energy at x equals 0 for the frictionless case. You can verify that. Therefore, all the kinetic energy has been transformed to internal energy by friction when the block arrives at x equals 0. And the speed at this point is v equals 0. In this situation, as well as that in part B, the speed of the block reaches a maximum at some position other than x equals 0. So this ends our discussion of the situations involving kinetic friction. Next, we will discuss section 8.4, changes in mechanical energy for non-conservative forces.